Welcome to Advanced Linear Algebra. Today we are diving into least squares approximation. Imagine you're a tailor trying to design a single one-size-fits-all shirt for three very different customers. You cannot possibly make one shirt that perfectly fits all three people at the same time. Instead, you must choose a size that minimizes the total looseness for everyone combined. In mathematics, we often face a very similar problem, and least squares is our ultimate tool for finding the best possible compromise. Now that we understand the basic idea, let us look at the math. In linear algebra, we frequently try to solve the matrix equation AX equals B. But what happens when we have more rows or equations than we have unknown variables? This is called an overdetermined system. Because we have too much conflicting information, no exact solution X works. Geometrically, this means our target vector B does not live in the column space of matrix A. Since we cannot reach B exactly, we try to reach a point inside the column space that is as close to B as possible. We call this best guess solution X hat. The difference between our target and our best guess is the error vector, E. So we have this error vector, and we want to make it as tiny as possible. How do we find this magical best guess X hat? Imagine standing on the floor and wanting to reach a light bulb floating in the air. The floor is our reachable column space, and the light bulb is our target B. The absolute shortest path from the light bulb to the floor is a straight line, dropping straight down, making a 90-degree angle with the floor. In linear algebra, we call this orthogonal. So for our error to be the smallest, the error vector must be completely perpendicular to every single column in matrix A. To truly cement this geometric idea of dropping straight down, let us look at it visually. Here we see a flat plane representing the column space of A, which is our reachable floor. The target vector B floats above it. The projection P, which is A times X hat, is the shadow of B cast straight down onto the plane. The dashed line is our error vector E, representing the vertical distance between them. Because it drops straight down at a 90-degree angle, it represents the absolute shortest possible distance between the target and the plane. This picture is the heart of least squares. This visual geometry leads us directly to the most important formula in this topic, the normal equations. This formula gives us the exact recipe to compute the best possible compromise solution, X hat. Here, A is our original matrix of coefficients and A transpose is that matrix flipped. The vector B is our unreachable target. By multiplying A transpose by A, we create a new well-behaved square matrix that we can invert. As the data in A or B changes, this formula automatically adjusts to find the new closest fit. If the target vector moves further away, the error increases. But this formula guarantees we still find the absolute closest point possible. Before we move on, let us see this formula in action with a concrete example. Suppose we have three data points on a graph, 1, 1, 2, 2, and 3, 2. We want to draw a straight line, y equals c plus dt, that best fits these points. If we plug these points into the line equation, we get three equations, but only two unknowns, c and d. This is an overdetermined system. We extract the coefficients to form matrix E. The first column is all ones for C, and the second column holds our t values. The vector B holds our target y values. Continuing with our calculation, we need to build the pieces for our normal equations. First, we find the transpose of A by turning its columns into rows. Next, we multiply A transpose by A. Notice the result is a symmetric 2 by 2 matrix, which confirms we are on the right track. Then, we multiply A transpose by our target vector B, compressing our target data into just two numbers. Finally, we calculate the inverse of A transpose A by finding its determinant, which is 6, swapping the diagonal elements, and flipping the signs of the off diagonals. Now we put it all together. We multiply our inverse matrix by A transpose B to find our final answer. The matrix multiplication gives us a top number of 2/3 for our best C value and a bottom number of 1/2 for our best D value. This means our best fitting line is y equals 2/3 plus 1/2 t. Even though this line does not perfectly hit any of the three original dots, it passes exactly through the middle of them, minimizing the overall vertical distance to all 3 points. Let us look at a slightly different geometric problem using the same formula. We want to find the orthogonal projection of a vector B floating in three-dimensional space onto a line spanned by vector A. Here, our matrix A is just a single column vector A. We want to find a scalar multiplier x hat. We define A and B and then compute our pieces. A transpose times E is just the dot product of the vector with itself, giving 3. A transpose times B is the dot product of the two vectors, which equals 9. With our scalar values computed, we plug them into the least squares formula. Since A transpose A is just the number 3, its inverse is simply the fraction 1/3. Multiplying 1/3 by 9 gives us exactly 3. This is our best guess multiplier. To find the actual closest point on the line, which we call the projection P, we multiply our original vector A by our multiplier 3. The resulting point, 3, 3, 3, is the exact spot on the line that is closest to the original floating point. We have successfully found the shortest distance. Now that we have used this formula twice, let us understand exactly where it comes from. We start with our foundational geometric idea. The error vector E must be orthogonal to our reachable space. In linear algebra, multiplying a transposed matrix by a vector and getting 0 means they are perfectly perpendicular. So we write A transpose times E equals 0. Next, we replace the error vector E with its actual definition, which is the target B minus our best attempt, A times x hat. We are simply stating the orthogonality condition in terms of the variable we want to solve for. Continuing our derivation, we distribute the A transpose term into the parentheses. This is just basic algebra expansion, setting the stage to isolate our unknown variable x hat. We move the negative term to the other side of the equal sign, arriving at the famous normal equations. This transforms our unsolvable system into a new solvable system. Finally, we isolate x hat by multiplying both sides by the inverse of A transpose E. This acts like division, allowing us to cancel it out on the left side, leaving us with our final beautiful formula. We have mathematically proven how to find the exact best compromise for any overdetermined system. This brings us to an important question. Why does this matter outside of a math class? In the real world, data is never perfect. Whether engineers are measuring battery voltage or economists are tracking housing prices, data points always have tiny errors or noise from faulty sensors. If we tried to find a mathematical rule that perfectly hit every single noisy data point, we would get a chaotic, useless zigzag. Least squares approximation allows computers to ignore the noise and find the true underlying trend, making accurate predictions about the future possible. Let us wrap up what we have learned today. First, least squares is our go-to method when an overdetermined system has no perfect solution. Second, it works by ensuring the error vector is completely orthogonal to our reachable space, guaranteeing the smallest possible mistake. Third, it achieves this by transforming an unsolvable system into the solvable normal equations. You have now covered the full topic, from the geometric intuition to the mathematical proof, understanding a concept that forms the very foundation of modern data fitting.